So welcome everybody to this knowledge sharing masterclass. And what are we going to talk about? It's actually what lies ahead for the subsea systems. We talked about it already, and welcome, Sohail. Welcome so much. And it's actually a knowledge sharing masterclass where senior experts share their view on the latest developments in the subsea cable industry. And this masterclass actually contains of 3 speakers from Corning, Alcatel Submarine Networks, and Infinera, which each an important and interesting submatter topic have for us. So again, a warm welcome. And we're going to do this a bit different. We're not going to be silent. I want this to be interactive. We need your feedback. We need your support. We need your knowledge to make this masterclass actually complete. Okay, is that a promise? Will you help us, please? Was that a yes? I didn't hear that. I want your commitment, guys. Come on, you can do this. Here we go. Thank you so much. I'm really, really happy for that. Now, we have 2 speakers here coming up, and in a minute I will ask them to come and join me. But to start off, you see, of course, Lydia here, of course, from Corning on screen. So I would like to give Lydia a warm welcome. And Lydia, maybe you can quickly introduce yourself and say something about yourself, the company, please.
For sure. First of all, thank you so much, Eric, for having me. It's a very pleasure for me to deliver this masterclass talk for innovations in fiber for subsea systems. So I'm Lydia Gaudino. I have recently moved into Corning, and my role in Corning is to drive innovations and future fiber for subsea long-haul transmission systems.
Thank you so much, and a very warm welcome. And please take this applause already. It's for you already. So here's your applause. And that's an upfront applause already, and you haven't started yet. So fantastic, Lydia. Thank you. Now, if I may invite Pascal, please join us from Alcatel, ladies and gentlemen. Thank you so much. And Alan from Infinera, please come. A fellow Dutch guy on stage, ladies and gentlemen. Thank you so much. And please get a seat. Please be so kind. Take a seat. Take the microphones, and Pascal, if I may ask you, please introduce yourself and say something about Alcatel if the people do not know yet.
Hi everybody, Pascal Pecci. I'm working for Alcatel since 25 years and for Alcatel Submarine Network for 10 years. So Alcatel Submarine Network is a well-known submarine cable provider. I'm really proud to be part of this team. And I would like to thank Omantel and specifically Willie George for inviting me to this masterclass. Thank you, Willie. You did a great job. So thank you very much.
Thank you so much, and please take a seat. And last but never ever least, Alan, please, floor is yours.
Thank you, Eric. My name is Alan Hollander. I am really pleased to be here, and I'm honored to be invited to be part of the masterclass. I work for Infinera. I'm in the industry for more than 20 years and with Infinera for at least 5 years. As part of the Subsea team, I'm heading up the global systems engineering team. Thank you very much. I hope to get good questions from you. Thank you.
Thank you so much, and also a warm welcome to you, Alan. Now, Pascal, I know you have something prepared for us and for the audience and to pay attention to, right? So you're talking about the evolution, right?
Yes, exactly. The evolution of the submarine network. As you may know, there are lots of evolution currently. And I hope at the end of the presentation, turnkey, open network, SDM will mean something for you. Because this is the current market, and we will see at the end of the presentation of also the future, what will come in the coming years.
Okay, thank you so much. And if I may ask you kindly to go already to the stand, and talk us through the evolution of the subsea networks. Thank you so much.
Thank you very much. So let's go. So evolution to open subsea cable. So Pascal Pecci, as I just said. So here is a menu of the presentation. So we will start from turnkey, the evolution from turnkey system to open cable. And then once we have presented this key evolution, this key recent evolution of the submarine cable, we will go through the equipment of submarine. So first the dry part with the portal, what we call the portal, then the wet, evolution of the wet, and we will do a focus on the evolution of the BU, branching unit, and also RODAM. And then the new parameters to evaluate the performance of submarine cable, because you will see that with turnkey, we used to have capacity and Q factor. With open system, we remove the submarine line terminal equipment, we remove the transponder. So we need to define new parameters to evaluate the performance of this cable. Then I will explain and I will show you what is the benefit that will bring a spatial division multiplexing. So how with more fiber pairs we can reduce the cost per bit, because I imagine for all of you the cost per bit is a key parameter to focus on. And then at the end of the presentation, I will conclude with the future of submarine cable. Evolution that will be driven by many parameters. We will see the number of fiber pair, the band that we will use, or even something that Lydia will talk about, core or multi-core fiber. So are you ready? Let's go through this presentation. And thank you very much. I'm not used to present with so many people.
Pascal, if I may quickly come, we'll listen to your presentation in 1 minute.
Okay.
And this is an interlude. One of the key guys who made this happen, the whole masterclass, and I want you to clap your hands for him, from Omantel. Here's Willie George.
Good afternoon, everybody. This was a bit last minute, so pardon any mistakes I make. So on behalf of carrier community and Omantel, I would like to welcome everybody to this inaugural knowledge sharing masterclass being held as part of GCCM. So I can see from the attendance that we have a very diverse audience, right? I can see members from suppliers, from integrators, from partner carriers, as well as members of academia. So on behalf of, the organizers, wishing you a very warm welcome, right? So I can see the participation has been really good. So thanks for that. See, one of the benefits of working for Omantel Wholesale is that we get to work on projects that require the latest and greatest, in technology. And one of the nice side effect of that is that we get to work with some of the most smartest, and interesting people in the industry. So the whole goal of the masterclass was to bring this expertise into the region and share their knowledge and experience, with the local telco community, right? So, I want to take this opportunity to thank Pascal, Lydia, and Alan for all the efforts that they've done and for taking time from their really busy schedule to be part of this, right? So thank you very much, and Eric, over to you.
Thank you so much, Willie.
I also need to point out that I'm not just the mastermind. I think the main contributor for me was my colleague Mondir. So it was actually his idea. Yeah, so I just need to let you know.
It's
Thanks.
always a team effort, and especially in Omantel. Always. That's why you always deliver. Pascal, please.
Let's
Floor
go.
is yours again.
Let's go. Thank you very much. So let's start with the turnkey, the evolution from turnkey to open cable. So turnkey, what does it mean exactly? If we go to our turnkey system, here I represented the submarine line terminal equipment on the left, then a portal, I will explain just after it, Then the submarine cable, represented by a fiber branching unit, a ROADM. So the key element of the key component of a submarine cable. Then again, a portal and a submarine line terminal. So a turnkey system, we are selling, ISAN or a competitor are selling everything from the terminal to the terminal. So it was really close. The design was really close, design of the wet part, the submarine part and the dry part, because in the past we were using dispersion management. So we were having different type of fiber in the network. So we need to design specific transponder. 10 years ago, even now 12 years ago, because it was in 2010, the coherent appeared and the coherent transponder completely changed the transmission. And with this, we can have an evolution of the submarine cable to what we call open system. So we can decorrelate the wet part from the dry part. So we can sell on one side the wet part, and as you know, because you are all managing a submarine cable, as you know, it takes some time between the moment that we are signing the contract and the moment we will have the provisional acceptance, and you can really use the cable. Usually it's between 2 to 3 years. And meanwhile, at the moment you will sign the contract, maybe you're not ready to know what will be the capacity, what will be the transponder that you will use. And you will sign this 6 months before probably the provisional acceptance. So that's why it's also really interesting to decorrelate the open system. So the wet part and the component that are on the terrestrial part that are called the portal, with respect to the submarine line terminal, because the submarine line terminal during 2 or 3 years will evolve. You will have a new generation on the market every 6 to 12 months. If you consider all the manufacturer of transponder, if you consider only one single manufacturer, it will be 1.5 years, maximum 2 years. So you want to extract from the submarine cable the more capacity. So you want to have the best submarine line terminal equipment. So that's why we have now on the market what we call, and this is the title of the presentation, Evolution to Open Subsea. Open because the submarine cable and the wet part will be open to any SLT. So here is the part with the turnkey system and the Q factor. The Q factor and the capacity are the two key parameters to evaluate the performance of your submarine cable. The capacity, 15, 18, 20 terabit currently, this is the standard. With SDM, we will see that it will be more 10 or 12 terabit per fiber pair. So per fiber pair, and then you multiply by the number of fiber pair. And to evaluate this capacity, you need also a criteria of quality. So quality Q factor. The Q factor will give you the quality of the transmission from one transponder to the other transponder. So, and here we have the SLT that will start the transmission, the power feed equipment that will bring the power to everything, from the cable to the branching unit to the repeater. And then again, we will, it is symmetric, so we will have on the other side a power feed equipment and a submarine line terminal. So on the cable, when you will transmit the optical information, you will also transmit a current that will provide the power to the WSS ROADM to switch the information, or the repeater to amplify the signal. Okay. Okay, I will do it manually. In addition to go from CLS, so cable landing station to cable landing station, we are more and more asked also to go to the POP, to the point of presence. So between the power feed equipment and the SLT, we can have 250, 300 kilometers. And in this case, you will need to add dry repeaters in order to have capacity that will go from the POP to the POP or POP to CLS. I didn't represent here all the possible combination. Two are enough. And the target when you do the design of this kind of network is to minimize the loss of capacity because a submarine cable costs a lot, 200, 300, 500 million. So you don't want to lose any capacity in the last 200, 300 kilometers that you will have to cross from the power feed equipment, the CLS, to the POP. So that's why we need to optimize this from a full point of view. So terrestrial part and submarine part. Okay. On the left side, I represented the key element of the turnkey, so the Q factor. And now, since we are moving to open system, we will have a new parameter that will be called GOSNR. So Gaussian OSNR, or generalized OSNR. I will explain just after what does it mean. But the key element that you should focus on is the SLT. On the left side, with turnkey, you have only one SLT that will give access to the information. On the right side, what you have first a portal. The portal will give you access to the sea. And then you can connect to this portal what you want. You can connect any SLT from any provider. For sure, you can connect an ASN SLT. That's why it is open, because you can connect the SLT that you want. And depending on the time, at the beginning of life of the system, maybe you will choose one provider. And after 5 or 10 years, because a submarine cable will last for 25 years, it's a long time. So probably you would like to change after 5 or 10 years, you will like to change the technology, or you would like to change the provider. And with the open technology, you will have this capability. And again, we can find exactly almost the same scheme, but the only point that will change will be the SLT will be replaced by an open portal on both sides. Usually it is on both sides, because if you go open on both sides. And this product can be put on the cable landing station, which is the end of the submarine cable, or it can be put on in the POP also to manage the capacity on the POP location. Okay, so now that we have the basis for the turnkey and the difference between the turnkey and the open cable. So turnkey, you buy everything from the start and you are linked to a submarine line terminal equipment. It's more difficult then to have an upgrade with another SLT provider. Open system, it has been defined recently, 4 years ago, roughly. There are papers on this topic that explain what is exactly the open system, and you can connect your cable to any SLT provider. So let's go through the equipment of a submarine cable. And we will start with the dry portal. So what is the different dry portal that we can have, the different use cases that we can find on the market? So the first one is what we call fiber portal. For fiber portal, it will give you access to the fiber. So what does it mean, give you access to the fiber? You have 2 boxes on the right side, 2 blue boxes, the SUPI and AMP. So SUPI for supervision of all the cable, supervision of the element of the wet part, so the repeater, for example, the branching unit, the WSS RODAM, that will allow you to give some flexibility to your submarine cable. And then you have an amplifier that will boost, that will launch all this dense WDM channel into the cable. And then you have a connection to a third-party SLT. It will be a third-party SLT or an SLT. And this is exclusive. It is or you need to select one or the other. And as soon as the SLT will be connected, the SLT provider should have to manage this spectrum because this is a fiber portal, and so the spectrum is fully managed by the SLT provider. If you want to increase the power on one channel or decrease the power on other channel, it will be managed by the SLT provider. Now you have another step, which is the wave portal. The wave portal will give you access to the fiber, But in addition, it will give you access to the spectrum within the fiber. That's why we call it wave. And to manage the wavelength, we can see one additional blue box, which is the WSS, wavelength selected switch. And with this WSS, we have a flex loading here, which is connected to the WSS here. And this flex loading will manage the spectrum. So if you don't have any capacity on this cable, then the flex loading, flexible loading, will fill the whole spectrum. And as soon as you will add some capacity, the noise will be removed to be replaced by capacity. So that's why it is called flex loading, because there will be an automation between the loading and the transponder that you will put. You can open a window of 1, 2, 3 nanometers, 10 nanometers, or gigahertz if you want, 1 terahertz. And then you will fill one part of the spectrum with SLT, with capacity, and the other part of the spectrum will be loaded with noise, thanks to flex loading. So the big advantage here is written here, spectrum sharing feature, if you want to share the spectrum within a network and you want to manage it, or spectrum policing also, because it's important if you sell a quarter of a fiber pair to one customer, you need to be sure that you will not exceed the power that is allocated to it. So that's why there is also a policing to be sure that a quarter of a fiber will have a dedicated power and the power will not increase, because if this power will be increased, then automatically the other part of the spectrum will have a quality of transmission that will be degraded, which is not possible. So that's why when you share the spectrum on a fiber pair with the WSS and the flexible loading and spectrum policing, you can really tune how you want with the limit that will be put the spectrum. And the last part, the last element that we have is a ROADM portal, because the first two are usually put on the edges from A to B. And if you have something in the middle, you want to have something in the middle, you can add a ROADM portal. And in this case, in the branches where you have 2 fiber pairs, for example, in the branches, one that will go west and the other one that will go east, we can find here on the ROADM portal a connection to, for example, one fiber that will go east and the other fiber that will go east. And in this case, you can manage the traffic here with what is called the ROADM portal. So all the architecture linked to portal, fiber, wave, and ROADM will give you access to the fiber or to the wavelength and will allow you to tune the spectrum. Once we have seen the dry part, we can switch to the wet part, and the first element on the wet part is the repeater. Currently, the average value is a repeater every 70-80 kilometers. We can see network a cable that can go up to 110, 120, but the average value is usually 75, because this is an optimization of cost also. We want to reduce the number of repeater, but we want to have also capacity. And currently what we are selling the more is 75 kilometers between the repeaters. So this repeater has a compact amplifier structure. It's mandatory, because we will see with SDM, we are increasing a lot the number of fiber pair. In the past, it was 4, then 8, now 16, and in the future, 24. We have already sold a cable with 24. So in the same housing, in the same size of the repeater, you need to put more and more amplifier. So you need to have some capacity. And for sure, it should be compatible with the power feed equipment that we just showed previously. And currently on the market, what we have is a power feed equipment of 15 kilovolt, and it can be filled. It is a bipolar feeding, plus minus. And as just said, this repeater is compatible with 24 fiber pair. And we have with this repeater inbound optical supervision that will allow to know the characteristic of the repeater at any time. So the input power, the output power of the repeater. If one pump, and we will see later on the pump that are in the repeater that will provide the optical power. If one pump will fail, you will need to integrate all repeaters to know which one has a pump that failed. Okay, so this is a key element of submarine cable, the repeater. And in this repeater, what is really new recently and a big change is what we call the pump farming. It was really a clever idea. It was not used since the architecture of the repeater was the same since, I would say, 20, 30 years. And recently we changed it because the power per fiber need to be reduced and the reliability of the repeater should be increased. So the idea was to follow the evolution of the pump, and the pump were providing more and more power. And the idea was to say, oh, we have lots of power. Why can't we share this power between the different fiber pair? Because we have too much power. If we will use two pumps or one pump for one fiber pair, it's impossible to use one pump for one fiber pair. Because if one pump will fail, automatically you will lose the fiber because you don't have any more optical powering. So the idea was to say, okay, we will think of a pool of pump. This pool of pump will be linked to a pool of fiber pair, and we will build an architecture between the two, an equivalent to a cross-connect, but here it will be a passive cross-connect, in order to increase the efficiency in the coupling, to increase the reliability of the amplifier and the repeater, and to have a wide range of optical power. And what does it mean when we have a wide range of optical power? So this is the power that we will launch into the fiber pair. It means that we can tune as we want when we will design the submarine cable. We can tune as we want the capacity. We can go from 8 to 10 to 15 to 20 to 25 terabit per fiber with exactly the same architecture of repeater, of amplifier, just by changing what is in the middle, the cross connector. So the way we will connect the pump and the fiber pair. So here is an example of connection. Here you have a pool of pump with 4 pumps. All these 4 pumps will provide an optical power. That then the first blue box is a 2x2 coupler. So the 2x2 coupler has very low losses. And the target of this 2x2 coupler is just to mix the power of P1 and P2. So you will mix this power, and then on the first stage, then you will mix the power of pump 3 and pump 4. And then with the second stage of the 2 blue boxes, you will then, since you have a cross connection in the middle, you will mix also the power of all branch of the first stage. So at the end, FP1, FP2 will receive a mix of P1, P2, P3, P4. And when you count here, we have an average value, 4 pumps, 2 fiber pair. So we have an average value of 2 pumps per fiber. When you have 2 pumps per fiber in a classical configuration, if you lose 1 pump, you will lose 3 dB in terms of power. So you will lose some capacity. And in this case, when you mix with the cross connect, when you mix the power of all the pump, then if you lose 1 pump, you will lose only a quarter of the power. So it will increase the capacity, it will maintain the capacity, and it will increase the reliability of the amplifier. And you can also reach architecture that was not possible in the past. As I said, 1 pump over 1 fiber is not possible, but 4 pumps over 4 fiber pair is something which is possible, because the reliability is excellent. Now that we saw the repeater, the evolution, the main evolution currently on the repeater with what is called the POM sharing. Let's go to the branching unit and the RODAM associated to it. So it's just a reminder here, because usually people are speaking of BU, thinking of BU RODAM altogether. So I just want to remind that we have two parts. When we have a branching unit, the branching unit will be here usually to divide the cable into two. So we have one input on the branching unit and two output usually. So and the branching unit has three legs. So the leg that will go to station A, station B, and the leg that will go to station C, the branch. And then on top of the branching unit, we can add a WSS RODAM, so reconfigurable optical add and drop multiplexer, in order to tune the spectrum of each fiber. A RODAM will bring flexibility in your network. If you want to have 100% of the fiber that will go from A to B, you will be express. We will see it soon. And if you want to drop 10%, 25% of the capacity, then you will go through the RODAM and you will tune the RODAM in such a way to reach your target. So here I created a table in light blue. The first two lines in light blue are related to the branching unit only, the branching unit part. So the first part is the branching unit alone, because you have cable where you just need the branching unit, because you know that one fiber will go from A to B and the other fiber will go from A to C, and that's all. You don't need to tune the spectrum within the fiber. So that's why you will lose a full fiber drop. That's why it's put FFD, full fiber drop. You manage the spectrum on the fiber granularity. And then if you want to go one step beyond, then you will go to the second column, which is FFD plus RODAM generation 1. You will couple your branching unit with a RODAM, and this RODAM, as a first step, can use fixed filter. So you will define from the start if you want to have 50% of the traffic that will be in express and 50% of the traffic that will be dropped. So you will define this fixed filter. I admit it's just for information, because currently we are no more selling this solution, but it is still existing on the market, because I remind you that submarine cable are made for 25 years. So this kind of architecture is still existing. And then we have the generation 2 of RODAM with a WSS, where you can really tune as you want with the granularity that you want, the quantity of spectrum that will be in express and the quantity of spectrum that will be dropped. 5%, 95, 50, 50, and you can tune it versus time. So usually we are not using 5 and 95, it's more 80, 20, 50, 50, something like that. And the last column is related to what I will present now, which is a big evolution for submarine, because like the repeater, we have a big evolution with POM sharing. On the branching unit side, we have recently a big evolution because it was the same since years. We have a big evolution with the possibility to manage the fiber granularity within the branching unit. So I will explain right now what does it mean. But first, here is an example of a branching unit on the upper right corner. You can see that in this branching unit, you have some fiber that will be in transit and some fiber so that will go from A to B, the upper fibers. And then you have fiber that can go from A to C or B to C. So the fiber that we call that fiber that are dropped. So if we just put the branching unit, it will be a full fiber drop. All the fiber will be dropped, and you cannot have access on the express side from A to B to this fiber. And then what you can do is that you can connect this branching unit to a generation 1 or generation 2 RODAM. And in addition to the passive aspect of the branching unit, you can add, you usually have an optical bypass that we can see on the lower right corner of this slide, where if there is a cut in the branch and you will lose the power in the branch, in the C, on the C leg, then there will be an automatic switch of the fiber that was going to C to maintain the traffic on the express. Because if you have a cut on the branch, you will lose the traffic in the branch, and you want to maintain the traffic on the trunk if you have a WSS RODAM after. But the main difference with what I will explain in a few slides is that this is an automatic optical bypass. It will work only when there will be a cut. Then you will have to send a ship, you will have to repair the branch. When it will be repaired, then you will send a command to switch back the traffic to the branch. Here is the kind of architecture, schematic view of the architecture that you can find on the submarine network. So the first one on the left is symmetrical configuration, or also called bidirectional, because we can see that, so we have A on the left side, B on the right side, and C below. So C can discuss with A and B in both directions for symmetrical. The main difference between these two architectures is that here we will need to double the number of fiber pair in the branch, because we can see that we have one fiber pair here, and here we will have two connections, so two fiber pairs. The advantage of having two fiber pairs is that you will have more capacity, but usually when you drop traffic in a branch, the branch will need less capacity. So in terms of cost optimization, we were asked to develop this kind of architecture that we call degree free, because here we have 3 legs, but a degree 4. Here we have 3 legs and a degree 3. So here we will have only one single fiber pair in the branch. So you will reduce the cost of the branch, but you will have less capacity. So if it is in line with the requirement, then this is another solution to have symmetrical configuration. And then you can have asymmetrical configuration or unidirectional configuration, where here you will have traffic from the branch just to the east or to the west, because you can have a branch that don't need to speak with the whole trunk A and B just on one side. For example, if we are here in Oman, we want to go only to Egypt and Europe, and we don't want to connect, for example, to India on the other parts. So we will select asymmetrical configuration. If now we want to have both connection, go to India and at the same time go to Egypt and Europe, then we will select symmetrical configuration. And here, this is what is new with respect to branching unit. And where it is new, this is what you can find in the center. Switch to trunk, switch to branch. It means that you have the possibility to command now your branching unit. It was something that was passive. Now you have the possibility to create, to build, to order a branching unit, to install it. And then depending on the customer that you will have, you will send a command to the branching unit, and you will select to have your fiber pair in express, like there, here on the right side, or dropped. And it can be very useful, for example, if you have a stub BU. If you have a stub BU, this BU will not exist at the beginning. You have a stub BU, and then when you will add the branch, you can say, okay, I add the branch, I want to have traffic in my branch, so I will switch the traffic. Or initially, the customer that you have would like to have one fiber pair, and this is a big customer that is growing fast. You would like to have a second fiber pair, so you will have the possibility to switch another fiber in this branch via a command. And this is something which is new, and for sure that can be combined with WSS RODAM. So now you have flexibility on the BU side, and you have flexibility on the RODAM side. So flexibility on the fiber pair level and flexibility on the wavelength level. And here is another interesting use of the branching unit. with the increase of number of fiber pair on the cable. So here, 24 fiber pair cable, we will reach 500 terabit, 1 petabit in the future. So it's a high risk for submarine cable, lots of capacity. So without this view that I just presented, if you have a cut, your traffic will be lost. And usually the cuts are close to the A and B, close to the shore. So if you put this XBU here, at the limit of the small water and deep water, then you will have the possibility with the XBU to have the traffic that will go from A1 to B. And if there is a cut, then with this view, you will send a command and you will have the possibility to switch the traffic. And so the risk that you will have, the investment that you have put in a 24 fiber pair cable or a cable with half petabit or 1 petabit, the risk will be really minimized with this architecture. So this XBU can be used for branching unit or can be used close to the shore and on both ends, A and B. We can have B1 and B2 also to minimize the risk associated to the cut. And in this case, you have time to send a ship to restore and to repair the cable between A1 and XBU. And then if you want, you can restore the traffic via a command. So now, one question.
A point-to-point network between A and B, if there is a cut, obviously we'll lose all the traffic. Now you're saying if we put in XBU, we can route, but what is A2? Is this another landing?
Yes, you need to think it from the start. So it can be from the start, but you can say, okay, I don't have my second landing from the start. I don't have the terrestrial link from the start, but what I can do, I can think of it. I can put the XBU. Here I will have a stub. And then after 2 or 3 years, I will negotiate the permit for this, and that I will put this second station, and then I will add this branch, like a branch.
Yeah.
Like a branch.
That's clear, but
So
it increases the cost a lot.
It increases the cost,
Yeah.
but if you want to increase the reliability of this, you will need to create A1, B1, and another cable 24 fiber pair. And if you compare the cost between 2 cable 24 fiber pair and 4 CLS with respect to 4 CLS because and 2 XBU, this solution usually the cost is lower.
Thank you.
And versus time, you can maximize your reliability with the first solution. And another architecture could be also to put A2, B2, XBU, and then connect the XBU. And you will have a loop, which is something which is robust in terrestrial, used in terrestrial. So now, after all this explanation with respect to the BU, evolution of BU, let's go to the new parameter for the performance, because we are in the open network, open subsea cable. Sorry. So the first parameter that you probably know because it is used on turnkey, it is used now also in open cable, this is VOSNR. So VOSNR is easy to calculate. It is in all, this is a parameter which is all submarine cable. It exists since a long time. There is a procedure to explain how to measure it, but it was not enough because we have removed the SLTE, we have removed the capacity. So we need to find something else to define the performance of this submarine cable. And so we use Shannon, the Shannon capacity. So Shannon explained that there is a formula, the capacity C, that can be calculated with respect to the bandwidth that we will have. So the bandwidth will be the bandwidth of the repeater and the noise that we will have, so the signal to noise that we will have on the wet part. And this wet noise will come from 2 elements. It will come from the amplifier, so the optical signal to noise ratio, because the amplifier will add some noise. But this noise will also come from the fiber. And when we are speaking of OSNR and GeoSNR, there is a new parameter which is used also, which is SNR. So we are removing the O, the optical, to go to SNR. Why? Because 5 years ago, all transponder, all manufacturers were roughly at 33 gigabaud, 30, 35 gigabaud, with a spacing of 35 gigahertz. So we were all speaking the same language. When we were speaking of OSNR, usually it was for 120 channel. Nowadays, you have different provider. We are in the open world. So one provider has double the gigabaud to go to 66 gigabaud. Another one has triple, or you have also many configuration that lies in between, So when you change the spacing, if you go if you change the number of channels, then automatically you will change the OSNR, and it's a mess to compare one submarine cable to another submarine cable, one provider with another provider. So the idea was to say, okay, let's normalize all this. This is a normalization, and we will consider the OSNR that is given by one provider. We will divide by the spacing, and it will give this formula, so the SNR, with the calculation that I put here, and all calculation will give exactly the same result, 10 dB. So no matter the provider that you will talk to, you can speak of SNR. You don't need to specify, okay, the OSNR, but how many channels, it's complex. I will speak of GSNR only. So the specification now in the submarine cable are almost all based on SNR. And once we have defined the SNR, we can use the Shannon formula. So the capacity, that will be in terabit of your cable, the bandwidth of the channel, the noise power, the signal power, and the Shannon capacity is the theory, if everything is perfect. But we are in the reality. So in the reality, what we have is we are using polarization division multiplexing. So this is a big advantage because we can double the capacity. So we can, because we have two polarization, we can double the capacity. But what we are doing when we are filling the spectrum in blue of the repeater, we have some empty spectrum, empty space. So we need to multiply this capacity by a filling ratio and remove 10% of the capacity. And then we need to consider also the noise coming from the transponder, so the modem, the fiber, the amplifier. So at the end, the formula of Shannon with the signal to noise ratio is in fact a concatenation of the noise coming from the amplifier plus the noise coming from the nonlinearity plus the noise coming from the modem. And all this will give, in fact, a formula where you have the signal to noise ratio that you will have at the end of the transmission. And this signal ratio will be linked to the dry part that I just explained with the portal on the transponder, and the wet part with the amplifier and the fiber. So it's just a summation of all these elements. And it's key to understand this because here I'm showing an example where we have exactly the same SNR for all the three configurations, so the gray dot. But depending on the OSNR, we have put a number of repeaters that was different, 120, 170, 300. And we can see here that we have the GeoSNR for all the configuration, and we can have almost 3 dB difference between the different configurations. So 3 dB is a lot of capacity that will be lost if you don't understand the SNR and GSNR concept and the design which is linked to it. So what will happen if this is the capacity versus the GSNR? For example, if you specify something that I explained previously, which is 10 dB for the GSNR, you should have this capacity according to Shannon. But now, if you consider the filling ratio, the capacity will be decreased because you need to remove 10%, roughly. Then you add the contribution of the modem. So you can see that your capacity is going down. And then the last step is to add all the imperfection of the transponder, and also the margin that you want to have, because usually you don't want to work at the FEC limit. If you work at the FEC limit, you will have the traffic, you will lose the traffic, you will have the traffic. So you need to work 0.5 or 1 dB above the limit. And as soon as you will add 0.5, 1 dB of margin, you will lose some capacity. And this is this arrow. As when you will add some dB here, you will lose some capacity. And when you look the 10 dB, finally you will have this capacity, and Shannon was predicting this capacity. So roughly, currently, if we look at the Shannon capacity, the transponder, the best one are around 60, 70% of the Shannon capacity. So the dark green line, and the other one are at 50% of the Shannon capacity. Now let's switch to spatial division multiplexing. What is the interest of spatial division multiplexing? Is to think, the idea is to think differently. We want to transmit, for example, 200 terabits. Will we use 8 fiber pairs at 25 terabits? So low number of fiber pairs with lots of capacity, or will we use 16 fiber pair with 12 terabit only? So here I plotted the cable Shannon capacity versus the power that we will put in the fiber. And here I put 2 pumps. So this is the capacity that I will have. I'd like to have more capacity. So my first possibility is to increase the number of pumps and to increase the power. So in this case, my capacity will increase by 20%. Now, if I double the number of fiber pair instead of increasing the power of the fiber, I can increase my capacity by 100%, which is logic. I double the number of fiber pair. But if I use 150 micron square fiber, which is the best fiber on the market, it has also a high cost. I will double the cost of my cable. So the idea is to switch to 80 micron square fiber that will have a lower cost. And we can see that we will lose only 15% of capacity. So at the end, when we compare this solution here with this solution here, it's better to double the number of fiber pair than to increase the power per fiber pair. So that's why we have an efficiency with SDM. And now I would say that we are at a level of 80% of submarine cable are SDM, and only 20% of submarine cable are turnkey system. So this is an excellent solution to increase the cable capacity, to be more power efficient, and also to concatenate this with a terrestrial link. So I will skip the commissioning part, and I will go directly to the future. So the future of submarine cable, what do we see currently for the future to keeps on increasing the capacity, but also the cost per bit? What we can consider is C-band. So currently all submarine cable has C-band, is to extend the band, so to go to L-band. We already have one cable that tested this solution. And it was not a big success. So currently C-band is a comfortable way to increase the capacity, but maybe in the future, it will be something that will be studied again. Another solution, we were having at the beginning 8 fiber pairs, then we switched to 16 fiber pair, 24 fiber pair currently, and in the future, I'm sure we will add 32 or 48 fiber pair. But we can also consider the fiber, sorry. And Lydia will have a topic on this, so we'll not enter into this. Currently, we have only single core fiber, but in the future, Lydia will explain you that we will have an evolution of the number of core in the fiber. So more core, more capacity. But to feed all this band, all this fiber pair, all this core, we will need also to change the power feed equipment because we will need more power to share between all this path. So more capacity at lower cost per bit. And what we can see also, it is already a reality, but there will be an evolution in the coming years with respect to sensing. So we are asking also to these submarine cable that are currently a telecom, that are mainly telecom, to add on top of their functionality, to reduce the cost, to add sensing. in order to detect earthquake, to detect with climate change, to detect the evolution of the temperature of the ocean, for example, and to collect many information for university and to have a better knowledge of the sea, better knowledge of the evolution of the sea. So that's why we are coupling more and more the sensing with telecom submarine cable. So here is what we just saw. Very quickly, sorry, lots of information to digest. This is an evolution of the submarine cable of the last, I would say, 10 years. So open to question.
Wow. Merci, Pascal. Thank you so much. Thank you so much. That was a lot of information, right? Are we still awake? Yeah. Do we have, as Pascal kindly asked, I mean, he's open for questions. Anybody having a question? Sohail, of course. Please.
Thank you.
Going back to XBC, the view. Understood?
Yeah.
Can we deploy this in the existing cables?
This is something that we are proposing currently. And so this is something that can be asked and proposed, yeah.
And are you open for other cables or only ASN cables? Like if the existing cable is not ASN?
Yes, so currently, yes, good question. I can ask if we can, so the idea would be if there is an existing submarine cable on the water, which is not an ASN one, can we deploy, cut this cable and add this XBU? I can ask.
I'm asking because I think Munder and they understand what I'm saying, because we have a cable. So the Gulf region is very shallow water. Start from Oman all the way to Kuwait. We are talking about a very shallow water, number of pipelines. And the problem is this is also, the corridor for oil. 40% of oil goes through this corridor. So what we see is the submarine cables that are domestic submarine cables connecting Oman with another part of Oman, because of shallow water fishing and then because of this whole thing, we are having cuts. So
Okay.
I think this is something that we are interested to see the option of landing Qasab. So
Okay.
that's why I'm asking, because we are talking about open cable. So
yeah, I will come back to you and we'll give you the link to the people that are managing this, and then you can discuss with them. For sure we are proposing it on our cable. On our foreign cable, I don't know if this is something that we are doing.
one more question on when we were talking about the pool of pumps.
Yeah.
Now, fiber pair 1 and fiber pair 2 both have 2 fibers. One is trans and receive.
Yeah. One is go and one is return.
coming,
Yes,
yeah?
exactly.
So what happens when one of the pump is down on slide number 16?
Yeah. So what happened?
Because these are hard-coded, right? These
yeah.
are hard-coded into pump 1 and pump
Yeah,
2.
exactly. So if we have 4 pumps, for example, and you will lose one pump, you will lose something like 0.3, 0.4 dB of power on one amplifier. But usually in a connection between A and B, you have 50, 100, 150 amplifier. So the impact on the traffic will be minimal, because losing 0.4 dB on one amplifier over 100, it's completely negligible. You will not see it.
Thank you.
Other questions, please? Thank you.
Yeah, I have a question in regards to the combining C and L bands. I see that a lot of R&D, mainly specifically, I would say they're going to the submarine, which is the start of the capacity building. But we don't have to forget the terrestrial cable, where we have to connect POPs within the country, for example, across the country. For example, we have between Muscat and Salalah, we have two landing stations, in which I assume a lot of capacity will be required between them. But to what extent now there's a development on the normal cable of G652, for example, where we have a super C band plus L. I know there is a lot of talk about additional 30% on top of what we have now. To what extent there is a promise to go to that direction in the terrestrial cable as well?
Okay. So the question is the extension from terrestrial to submarine?
Exactly. So for the terrestrial, now mainly you talk about the submarine, the C combined with
Yeah.
L, and there is a super C now they're talking even.
Yeah, yeah.
And there is a promise of additional 30% of the capacity, but mainly in the submarine side. But we don't have to forget the terrestrial cable where we're connecting POPs together as a transit traffic between them. So my question is there is an R&D is going to that direction as well for the G652, for the normal cable of the terrestrial, or you mainly focus on the submarine?
No, because in terrestrial, when I'm speaking of submarine, now the fiber that we are using in submarine and the fiber which is used G652 SMF in terrestrial are really close. So transmitting C+L in terrestrial is already existing. In terrestrial, lots of terrestrial network, Luca can say it, are already providing C+L. So it's possible to upgrade a terrestrial network in C+L and then have C+L also on submarine, maybe in the future, because it will compete with more fiber pairs and with multi-core. And another solution would be to say, okay, I have many fiber pairs on terrestrial. Why the number of fiber pairs compared to terrestrial in submarine is limited? Because in terrestrial, it can be 1,000 fiber pairs. While in terrestrial, we are at a maximum currently 24 fiber pairs. So if you multiply the band, then you can be C on the terrestrial part. And then when you arrive in submarine, you switch to C+L in order to increase the capacity. We should think of capacity more than C and L band and the way we will transmit the signal. I strongly believe that in the future, we will go to higher fiber pair and higher core than C+L. Why? Because in fact, it's easier to sell or to swap fiber pair with less capacity. So 10, 12 terabit. If we go to C+L, then we will have a big fiber with 30 or 40 terabit per fiber. And then automatically to sell, it's more difficult.
Yeah, another question is in terms of opening the multiplexers plus the OT, and this is the talk of mixing between vendors within the same platform. To what extent is like 100% is achieved in terms of maintaining protocols, operation maintenance, and everything is maintained? No need to go, for example, a single vendor, everything. Because always you'll find the single vendor, there is an advantages. If you do the mix, you will lose these advantages. To what extent that barriers start being narrow and narrow?
Okay. I hope, yes, it will be narrow. With Nokia, we have also SLT. We are manufacturing terrestrial part and SLT and submarine part. So we try to close the gap between terrestrial and submarine. Yeah.
All right.
Yes.
Thank you so much. We have a question all in the back. So and Bartosz, while you're going there, I'll have a quick question in between. So if that's on the new parameters, SNR and channel capacity formula, are they used by many customers?
Yes. Currently, all open systems are using SNR and the Shannon capacity. They are the Shannon capacity formula that I explained here is the formula that you will find in the technical specification of contract in order to be sure that all manufacturers of submarine cable will use the same formula. So this is this one. And with SNR to be sure that we will decorrelate the transponder from the wet.
Just
so, yes.
to know what to expect, huh?
Yeah, exactly.
From you guys.
Exactly.
Thank you so much. Question from the gentleman in the back,
Yes.
please.
Ahmed from Omantel operation.
Hello.
As I know, the open system is using now aluminum power conductor, and this have advantage more than the copper. What is the advantage? Again, like Dr. Ali answered, I also interested terrestrial. What evaluation we can in evaluation in future? We can find one node in dry will be used with terrestrial and submarine together. In wet station, one node can carry the both direction, one terrestrial and one here to reduce the cost. Is this be happened soon?
Okay. Yes. So the fact that we can split the traffic one direction of the other is something that is a reality. With respect to the question of aluminium, yes, we are proposing copper and aluminium, and an aluminium cable is already existing between England and Denmark, 600 kilometers, and we are currently manufacturing 3,000 kilometers of this aluminium cable. So what is the benefit of this cable? The resistivity is higher with respect to copper, but the big advantage of this one is the cost, because aluminium is cheaper than copper. And also the big difference is the variation of the price. Copper price currently are going up by 30, 50, 60%. When at the moment you sign the contract and 1 year later, you can have an increase of the price of copper by 50, 60%, while aluminum is more stable, only 10, 20%. So this is really important from a cost point of view. Then for the future, when we will go to 24, when we will go to 32, 48 fiber pair, we will need to decrease the resistivity to go to 1 ohm, 0.8 ohm per kilometers for the cable, to minimize the loss of the cable. And so it means increasing the thickness of the conductor. With copper, it will increase a lot the cost of the cable. With aluminum, it will be better. So that's why we tested this new material, aluminum, and we validated, after 5 years of study, we validated with this conductor. And this is not something that we are proposing right now for all cable, because copper is working well till 24 fiber pair. But for future, we are sure we are ready.
Okay, fantastic. Thank you for the questions. Any other questions? One question. Last one. For you? Okay. Microphone is coming. The microphone is coming. So the complete audience will hear your question. Thank you.
Yusuf from Omantel. Regarding the XPU, instead we have like terminal A and terminal B for using the XPU. Can we have like terminal A and then another pitch main hole? From that pitch main hole, we are station,
Okay.
rather than have a new building station with all equipment. So
Yeah, but in this case, will you protect from the cut that you will have under the water?
so the XPU, it will be inside the water.
Yes.
Then we'll have the protection to the another main hole, so which is far away from the
Yes, correct. Yeah, correct.
rather than having new buildings or station.
Mm. Okay, beach manhole and then come back to. Oh yes, excellent idea. Yeah, why not? Why not? Yes, this is another possibility. Knowing that it should be far away to be sure.
Yeah.
To be sure that the ship that will cut the first cable will not cut the second one at the same time. Mm.
Okay. Thank you so much. Sorry, Bartosz, there was another question you said? Okay. Last one, and then we're gonna move on to the second.
Yes, because I'm over time.
The last question is regarding the R&D of the future cable.
Yeah.
Have you considered to be building more environment friendly cable, like sustainability and all this? Because we know the life cycle of the cable is 25 years. So is there any another solution for this?
So in terms of solution, during years, we have recycled the cable. So what does it mean when we are laying a cable? At the end of the laying the cable, the ship will be empty. So we are recovering cable that are under the water. So it's something which is green, and then we bring it back to our manufacturing in France to recycle the cable, to recover the copper and so on. And with respect to the green aspect of the new cable is we are working a lot on the efficiency of the pump, and that's why we are reducing the power per fiber.
Okay, thank you so much. And with this, Pascal, I know it was almost an hour, and
Yeah, sorry,
we're running late already. But you know what? Whenever something is interesting, you forget the time, right? So that's my fault. But anyway, thank you very much for your questions, and a big applause for Pascal. Merci.
Thank you very much. Shukran.
Thank you so much. And with this, Lydia.
Hello.
Hello. Sorry to keep you waiting so long. Apologies for that.
It was exciting, Pascal talked.
Yeah, he's always exciting, right? To tell us how is going? So Lydia, tell us, what is your presentation about? What is your topic? What are you sharing with us?
Okay, so are you seeing my sharing my screen now?
Yes, it's coming.
It's coming.
Okie dokie.
Okie dokie.
So, all right. So, guys, are we ready for Lydia? Yes, they are. Okay, Lydia, please take it away. Good luck, and we'll have a couple of questions afterwards for you from the audience. So, thank you and good luck.
Thank you so much. I guess my talk is going to build on Pascal's talk, but I'm going to be focused more in, on the role of the optical fiber and types of optical fiber for subseas and terrestrial extension systems. And, so the agenda is starting talking about subsea fiber technology today, how fiber is contributing to high capacity systems. And then I'm going to move on to subsea network integration from subsea to terrestrial systems, and finalize my talk with fiber innovation pathway, future fiber technology. And what is so excited about our field is just optical fibers are everywhere. So 99% of the global traffic communication is carried by an optical fiber. And I think this is fascinating. And this is what is happening today. We have around 350 active cables, submarine cables, and around 1,000 kilometers of new cables are laid every single year. And if you have a look closer, to the region, so those are the all new landing station in Africa and Middle East between 2021 and 2023. And if you have a closer look to Oman, look how many new stations, new hyperscale data centers are we having in the region in only 3 years. That is just amazing how fast, this field is growing. And what brings me, so the question that we have is, why this has happened? We basically have an endless race for capacity. And this is because we have, a virtual cycles. More application do we have, more capacity is needed, then more capacity is proposed, and there we go. And we have this driven for a high capacity system since, the first submarine cable 150 years ago. So the question that I raise is, how can we increase fiber capacity or cable capacity? And, Pascal brought this, the Shannon equation in his talk, and he kindly and very well explaining the role of this equation. And what I'm going to focus on my talk is how optical fiber plays a role on the Shannon equations, right? Which, as he said, we can improve signal and noise, signal to noise ratio, or GSNR, as is the metric used for, the submarine cables. So how the right fiber can improve that signal to noise ratio. Pascal also mentioned the bandwidth. The two, as he said, we have, two polarization. We can transmit the information of two orthogonal polarization on the light. And also what I have added here on the equation, I think Pascal didn't have, is a spatial path. This means, or we can have multi-core fibers or parallel fibers, as Pascal said, 24 fiber pairs, 12, 48 fiber pairs. And fiber and cables path the ways to those high capacity systems. So looking at, to fiber innovations, what we have today is what is important in terms of fiber parameters. So very ultra low loss attenuation is really important to improve signal to noise ratio, right? Because you have lower loss, you have high power and compared to the noise. And also important for bandwidth, transmission bandwidth, right? Nowadays we have C band, but we can potentially go to C+L band. We have C+L band system, but we, lower attenuation across a wider wavelength range is really important. It's play important role. I will also touch base on the large effective area and how that can maximize the signal to noise ratio, the metric used to maximize system performance, or as Pascal said, GSNR. And finally, I also want to mention bending. So sometimes when, system people like us, people don't talk about bending, but bending, very important bending characteristics, improves a lot, fiber performance and system performance, because if you have very good in bending, you can, of course, maximize your signal to noise ratio, and also, of course, increasing bandwidth. And finally, I'm going to talk about fiber diameters and how that maximize cable capacity. For future path innovation, I'm going to touch base on multi-core fibers. It's a very hot topic now. Coupled core, multi-core fiber, few mode fibers, and the more disrupted technology, which can be hollow core fiber. And all of them, what is nice from multi-core fibers, they play a role in increasing the number of pathway, which increase linearly with capacity. So starting with low attenuation. Attenuation is important, and silica core fibers, what has enabled ultra low loss attenuation. If we compare here on the graph on the left side, we have the same attenuation for silica fiber, and today the typical attenuation for silica fiber is 0.183 dB per kilometers, while the typical attenuation for silica core fiber has gone down to is around 0.156 dB per kilometers, and a record of fiber attenuation has been shown in this paper, which is 0.1419 dB per kilometers. And on the right side, you can see the evolution of attenuation over the years, and it's pretty much very, very minimal decrease in attenuation has happened over the last 5 years, or 10 years, but it's difficult, but probably not impossible to further reduce the attenuation of the fibers. So effective area. So how effective area can impact signal to noise ratio? How can we maximize signal to noise ratio by increasing the effective area of the fiber? So what you're seeing here, this is what we call, so what is effective area? Effective areas is the cross section of the fiber where the light is transmitted through. And what's happening in a fiber, in a silica core fiber, when the core on the silica core fiber is exposed to high power, it generates a nonlinear response of the silica. So this means that if you look on this graph, we have signal to noise ratio versus power. In a linear system, like as a dotted line, if we increase power, we keep increasing signal to noise ratio and defer capacity. However, in a silica fiber, when you increase too much the power, you increase the power spectral density of the cable, so you reach optimum power that tells you what is the maximum SNR and what power your system should be operated. So when you have large effective area fiber, it reduces the power spectral density inside the core. It consequently suppresses the nonlinear effects. So in other words, it means that you can launch more power into the fiber and get a higher SNR compared to the regular effective area fiber. That's how we maximize signal to noise ratio. Moving on to bending. Why is bending important? Because bending, if you think about this analogy, the light is confined in a high index region. So if you have a bending on your fiber, so there's the photons can escape. So this means that when you bend the fiber, if you have a good bending diameter, you can reduce the loss. You don't lose too much signal to noise ratio because you lose less power compared to increased loss for higher tighter bands. So it's really important to choose a fiber with good band characteristics. Finally, from the established, what we have available today is how they play a role. for maximizing capacity is fiber diameters, small fibers. Specifically for submarine cables, it's been a game changing for today's technology, because the established, fiber for submarine cables has been 125 micros cladding diameters with 150 micro coating diameters. And today's technology, we have managed to reduce the coating diameters to 200 micron. And what this means, by reducing the coating diameters from 250 to 200 micros, we can increase in 50% the fiber count in a submarine cable. So for example, in a 7mm cable design, you increase the number of fiber pairs from 16 to 24. So it's really, really important message, because 200 micros pretty much doubles the typical fiber capacity and decrease the cost per bit for the same cable design, same cable size. And most important, it satisfies the near and mid-term submarine industrial needs. Okay, I think for now I have finished, all the technology that we have today and how they're important for maximizing cable and fiber capacity. Now I'm going to go to the second part of this talk, which is talking about subsea network integration. So subsea networks are becoming more integrated, right? So what this means, instead of having a landing station and an optical electro-optical converted from on the sea side, we remove that and we have express routes from the POP to POP, or point of presence or data center. And this is important. Fibers, the choosing of the right fibers plays a major role in maximizing capacity and preserving the submarine cost, and low loss and high effective area fiber in the terrestrial section is going to enable to preserve the submarine quality and protect the high value of subsea capacity. As Pascal mentioned, it's really, really expensive subsea systems. And another motivation to do that is if you remove the regeneration for the short line, you can see here again on this, it's becoming very crowded. A lot of space is needed on the shore. So if you choose to remove the regenerate and have a subsea integration, you're not going to need any space required at landing stations. You eliminate the expensive regenerators. We improve data security because you don't need to convert the signals from optical to electrical and electrical optical again. And finally, you terminate the data traffic direct into the terrestrial data center. And this can possibly minimize the cost per bit. And again, also another important parameter is the latency. As you don't have optical electro-optical conversion, you minimize the latency on this system. Another point is sometimes you have you can choose if you do want or you do not want a terrestrial extension, but sometimes geographically you don't have an option. If you do want to connect the traffic from Europe, to Oman, for example, or even going through the Red Sea or the Mediterranean, geographically you need to carry the traffic through terrestrial path. So it's really important. The point that I want to make on this talk today, I'm going to do a technical economic analysis of the terrestrial extension for these subsea routes. So the aim of this part of the talk is to investigate the benefits of using ultra low loss and large effective area fiber in the terrestrial section of the point of presence route to preserve the high value of the subsea traffic. In other words, what I'm saying, what are the gains in cable capacity and the total system value in millions per dollar for different terrestrial length, right? So here's an example. If you have the submarine cable connecting Muscat to Perth in Australia, right? What I'm saying, if we can actually not having the landing station in Muscat, for example, and connecting straight the submarine cable to a point of presence nearby. So here I just, create what could be a, inside network in the Middle East. So the system that I'm analyzing is, so the submarine route is 10,000 kilometers, cable linking Muscat to Penny. So the system design for the submarine link, I based my system design on this paper from Subcom, where they publish, what are the best submarine design system for different route length. And for 10,000 kilometers, it guided me to say that the repeater space should be 90 kilometers. The launch power should be operated 2 dB lower than optimum launch power. So it means instead of operating at the peak point, we operate the power 2 dB lower. And the number of fiber pairs for this cable should be 18 fiber pairs. For the terrestrial system, I'm going to be investigating the performance for 3 different fibers. I'm going to investigate the performance first for the legacy fiber, the G665, and I chose attenuation of 0.25 dB per kilometers. This is mainly because this is a legacy fiber that might be on the ground for 10 years, 20 years, or even 25 years. So that has been through a lot of repairs. So the attenuation of the past might have increased a lot. So that's why this is what is expected from a legacy fiber. I'm also compared to the best-in-class terrestrial fiber, which has attenuation of 0.183 dB per kilometers and an effective area of 8 micrometers square. And I'm going to compare this best-in-class terrestrial fiber with the ultra-low loss and large effective area fiber, G654E, which has attenuation of 0.166 dB per kilometers and 135 micrometers square effective area. For the submarine fiber, I have chosen, a best-in-class submarine fiber with 0.15 dB per kilometer loss and 150 micrometers square effective area. So going to our analysis, so what I'm showing here now is the capacity per cable in terabits per second for different terrestrial length extension from 100 to 1,000 kilometers going through a 10,000 kilometer submarine cable. And I have the 3 different fibers, as I mentioned before. So the blue one is the best, is the ultra low loss and large effective area fiber. The triangle ones are the best in class terrestrial fiber, and the G655 is the legacy fiber on the ground. And what this is showing us, it's clearly that the right choice of fiber is going to enable you to maximize the cable capacity and preserve the high value of the submarine cable. If we look at the next graph, which this is pretty much the cable capacity gains, the G654E capacity gains, it's pretty much when I do this one minus this and this one minus this, I have the capacity gain for the ultra low loss and large effective area fiber. So those are the gains relative to the best in class terrestrial fibers. So the gains in capacity can go up to 20 terabits per second, while if you choose to have a terrestrial extension and you have the fiber on the ground, but you choose to use that fiber, you're losing about 10 terabits per second compared to if you had chose to use a ultra low loss and high effective area fiber. So it's clear telling us that it's really important to choose the right fiber for the terrestrial extension if you choose to do so. This is nice. It's nice to understand the gains in capacity, but ultimately, what we want to do, what we want to know is what are those gains in terabits per second means in terms of total system values in millions of dollars. And that's the analogy that I'm going to make now. In order to do so, I use this this resource. So in the telegeograph, they say that usually a submarine cable costs around $30,000 per kilometers. So if I extend these $30 per kilometers and a subsea route from 5,000 to 50,000, I have a linear gain in the cost of the subsea project. And for our case, we chose a subsea route length of 10,000 kilometers, which means that this 10,000 kilometers is going to cost $300 million to be built. Now, we want to understand what is the value in terabits per second for these subsea costs. So pretty much what I do is I know that the cost, the subsea, I just use the subsea project cost divided by subsea cable capacity. So by doing my analysis of the cable capacity, as I mentioned the system design before, cable capacity has 381 terabits per second. So if I divide subsea project cost by the subsea cable capacity, the cost per terabit in this cable is $75 million, right? And this is important. So this is how I built this, blue curve on the cost per terabit. And for 10,000, that's the capacity. So if we go further and we try to understand what's the value in dollar, for different fiber used on the extension terrestrial route, we have the subsea project cost divided by the cable capacity times the delta capacity, in this case between the ultra low loss and large effective area fiber compared to the best in class terrestrial fiber. So the project, the total value cost gain is $108 million value gain if you choose to use ultra low loss fiber and large effective area fiber. If you do compare the system gain value for the ultra low loss large effective area compared to legacy fiber on the ground, it can provide up to $80 million gain in value for these systems. And to summarize these sections, I just want to say that landing in subsea integration systems improving data security and eliminate the expensive landing station regenerators. And the right choice for terrestrial fiber types can significantly improve the point of presence system value and reduce the cost per bit. The last part of my talk, I'm going to touch base on fiber future innovation pathway. As I mentioned, I have previously talked about all the established, technology and innovation that we have today. Now I'm going to touch base on coupled core, multi-core, few mode fibers, and then later on hollow core fibers. So, if you do a quick search on the Google image, you're going to have different flavors of different types of multi-core fibers, which what we call SDM or SDM fiber approach. And the research in multi-core fibers, has been going on for more than 10 years now. A lot of experimental lab test bed has been demonstrated with 10 pentabits per second multi-core fiber capacity. A lot of innovation has happened. But if we focus first, applications for multi-core fibers, specifically for submarine systems, I would say that, we might start with 1x2 cores or 2x2 or 2 cores or 4 cores fibers because, industry needs to start somewhere. It's a really revolutionary approach going for multi-core fiber. And if we look at, the roadmap, because today we talk a lot about, what are the roadmap for 1 to 5 pentabits cable capacity, transatlantic in 10,000 in 6,000 kilometers cables. And what do we have today? What can deliver today? With 24 fiber pairs cable and 200 micron fiber diameter, you can have around 0.5, 0.6 pentabit per second on this cable. But what are the possibilities in technology to further increase cable capacity? So if we look in a more revolutionary way with a 2-core fibers, this capacity can be increased for 1 pentabit per second. If we do have 4-core fibers, we might achieve 2 pentabit per second. And then you have the question, how can we go beyond 2 pentabits per second? What is going to be the next advanced or the next revolutionary technology? But as Pascal also mentioned, another, approach to keep increasing cable capacity, you can increase the number of fiber pairs and, deliver 1 pentabit per second. You can use, the 32 fiber pairs, C+L band, and also get 2 pentabits per second. Again, not clear how we're going to get to 3 pentabits per second. So this is an ongoing field, a lot of is in stake, and it's very excited. If you want to have a 5 pentabit cable by 2030, in 7 years time, which is what, industry is asking for. This is all from the fiber side, but as Pascal mentioned, electrical power must improve. A combination of, power feed voltage, aluminum cabinets, or mid-ocean powering, power efficient multi-core amplifiers are all necessaries, all different approaches that can help to maximize cable capacity. And I think, as Pascal said, aluminum is a very good, must be the best way to go forward when we increase the number of fiber pairs. Let's see, we're waiting for that, Pascal. Right, and the last section of my talk is hollow core fiber. Hollow core fibers, can be a very disruptive technology because, today, it has been proven that has 33% low latency, has about 10% low dispersion, and more than 3 orders of magnitude lower OSNR, and huge transmission bandwidth. Yeah, and today, so this is all and today has been proved parity with silica core fiber, very similar low attenuation compared to silica core fibers. It has a lot of potentials in many areas. It's unlikely to appear in subsea soon due to difficulties and large volumes and long spool length. So there's a lot of research to be done, a lot of things to be proved, but there's, a lot of potential. And I want to spend some time here compare, hollow core fiber in terms of ecosystem challenges compared to silica core fiber. So silica core fiber, we have more than 5 billion kilometers of installed solid core silica fibers. All the whole ecosystem needed for cabling, connectors, transponders, splice, amplifiers, large scale manufacturing, which is really important. It's been established with more than 5 billion kilometers of fiber. If we look to the ecosystem of hollow core fiber, if we think there's two network installed, hollow core fiber to date, I think it's just a small section, has been proven that hollow core fibers, works well with commercial transponders. Maybe Alan was going to touch base on that. But there's a lot of to be sorted out and improved on the whole installation ecosystem. Like we don't, proper splices, low loss splicing, connectors, cabling, testing measurements, crafting, training, amplifiers for those kind of fibers, and also, large scale manufacture for those fibers. So it's still a lot of research to be done, a lot to be proven, but a very exciting. I'm very excited by hollow core fiber and very disruptive technology. And I hope all of this is going to be proven one day. To summarize my talk, subsea optical fibers used today offer very low attenuation, large effective area, and superior bending performance. This has become possible because we have decades and decades of innovation in this fiber industry. The terrestrial extension of subsea routes is an attractive solution to improve data security and reduce the cost per bit. When combining the 200 miles coatings with today's optical fiber technology, we can satisfy the needs of the industry, develop around 0.5, 0.6 petabit per second in a transatlantic cable. In the long term, subsea systems may require further fiber innovations. Multi-core fiber is a contender to achieve ultra high capacity cables, although it might come with a premium cost per bit. Hollow-core fiber is a very promising, but still in early research. Very promising technology. Thank you so much for your attention. That's the end of my presentation.
Wow, Lydia, fantastic. And the applause was completely yours. And the speed you took us with you in your presentation is astonishing. So congratulations on this one, and fantastic. Let's see if there are any questions from the people, from the audience. Do we have one question coming? Of course we do. Please.
Sorry, I'll keep asking question always.
No, that's good. That's what we're here for. It's a masterclass.
Yeah, in terms of the cost saving, or mainly people are looking at the bits per kilometers, or the cost saving. But the only thing what I'm trying to say, we don't looking at the fiber, which is the main component. But I think maybe I will complement one of my colleagues' question when we talk about the environment. I think we have to look at the TCO, whereas the power is, I think, is the main point here, is the power as well, more than the capex. The operational cost, I think we have to consider more as well. So to what extent, I mean, away from the cables, even from the equipments, they push more to the R&D to reduce the emissions and the power, whereas the cost saving will be there if you look at the TCO. My second question maybe could be silly, but I'm curious to understand. When you look, show us the bend, and there is I would say the light is going out of the bend, if there is a curve. I got some questions directly. To what extent that light can be used as an information by the hackers for the interception? Is it that true? I would challenge them because of the keys and encryption, the speed of the keys, so many things. But to what extent that true? Is that out of cables light can be used as intercept signal as well? Thank you.
Thank you for your question. I'm going to answer the last one first. I agree with you, because it's also important for security, the bending, because as you said, if you're more bending resistant, less fiber is going to leak out. So you have higher SNR. And also probably, I'm not expert on tapping, but if you do have less power, I mean, I would say you're going to have a better receiver sensitivity to be able to detect the information. So I agree with you. You're right. For security is also important. Did I answer your question?
Yeah, you answered. Thank you.
Yeah, thank you for your comment. For the first question, I'm not sure if I understood. I think you were saying about power saving for the whole TCO cost, right? Yeah, I think Pascal is more expert on that. What I did for this analysis, which I follow this paper from Subcon, you do have different optimum power operation for different route length. So you choose what is the optimum repeater space in optimum power. So in this case, to have 18 fiber pairs in 10,000 kilometers, this repeater space, the power operation is going more to the linear regime. So I think it's a case by Pascal, maybe you want to complement, but I think it's a case by case study. Depends what is your subsea route length to maximize TCO capacity, to maximize to get a better cost per bit per TCO.
Okay, perfect. Bartosz, if I may ask you to bring the microphone to Pascal, because and thank you, Lydia. So Pascal can add to it, to the question.
Yes, Lydia, you are correct. When we do an optimization of a system, you have multiple parameters. This is a multi-dimensional optimization, and you consider the distance, and then depending on the capacity that you want, you will vary the number of fiber pair, You will vary the distance between the repeater. You will vary the type of fiber that Lydia presented, 80 microsquare, 110, 150, and then you will plot a curve that will give you an optimum with respect to the capacity that you want, and there is an optimum in terms of cost per bit when you will change all this. So this is a multi-dimensional optimization with a specific tool that we have, and we feed this tool with also the different parameter, and what is key also is automatically the cost of the repeater, cost of the cable, cost of the fiber. When you change the type of fiber, you change the way you transmit, but you change also the cost of the fiber. So that's why this is an optimization of all this, and it is linked to the distance and the capacity that you want.
Okay. Any other questions? Lydia, I have one for you. Am I
Yes.
allowed? Am I
Of
allowed to
course.
ask you a question? Yeah. Oh, thank you. Can you highlight the single most important fiber technology that would be heavily utilized over the coming 5, 10 years? What have you?
200 micros coating diameter fiber. It's just, you just almost double cable capacity for the same cable size. It's just ready, it's here, and it's, just doubling the capacity. That's what I see the way industry is going.
Okay, cool. Thank you so much. No other questions?
Yeah.
Sorry, the microphone will come to you. One last question for you, Lydia, coming up.
Okay,
Yes.
because I'm the only one maybe asking too much. Is there, because there's a talk about the vacuum transmission, where is the transmission over the vacuum?
Yes.
Whereas I think you're gonna have, in the future, you're gonna have tubes instead of silicons. To what extent do you think that it's gonna launch soon commercially, or this is like still an R&D, it's a dream gonna come true soon? Or
Well, I'm a believer. I was, I've been a researcher, was a researcher for 10 years old. And I think when you're talking about, you're talking about hollow core fibers, right? I just love this technology, and I really hope it can deliver the potential that it has. It can transform. It's not going to solve capacity problem, because it's really hard to do. With multi-core fibers, you increase linear capacity by increasing the number of cores. That's not the case for hollow core fiber. It's not clear if you can have a multi-core hollow core fiber. Probably not. I guess that's what I hear. That's not viable. So it doesn't solve capacity problems, but it's I think it's impressive technology. I hope it can deliver. It's promising, but I think we should, there's a lot of research years ahead of us before it can become close to a reality, to have this in large scale.
thank you.
Yeah.
Okay. Thank you very much. And then Lydia, please embrace the applause which is coming ahead to you from the audience here. And thank you so much for your heart, for your knowledge and energy and devotion on this topic. So thank you so much, and really appreciate it that you have been with us again, sharing the knowledge and making people more clever. So thank you so much, Lydia. Fantastic.
Thank you.
Thank you. All right. We go to Alan. Alan from Infinera. The floor is yours.
Is it working? Yes.
Yes, it is.
So exciting presentations from Pascal and Lydia. If Pascal and Lydia explain to you how to build a fast racetrack and the best tarmac, I will talk to you about the racing engine, the Ferrari, or maybe you are a Mercedes, or maybe you are a Red Bull fan.
I'm Dutch, so it's Max Verstappen who's world champion, of course. Of course, sorry.
So let's see if it works. Yes, it's okay. So my presentation will be about advances in transponder technology, the engines, and approaches to subsea cable upgrades. So how can we have different types of cars competing against each other on the same racetrack. Before I introduce some details to you, I cover details to you, I'd like to introduce some basics to you. So this is a kind of back to school, 1 or 2 slides, and forgive me for explaining maybe some very basic things, but it might be very useful for some of you who are not really intimate with some of the technologies that we are going to cover. So before 2010, transmission was very simple. You had a laser, you switched the laser on or off, and off was a 0 and on was a 1. And in this way, you can transmit data with a data rate of up to 10 gigabit per second. As of 2010, coherent transmitters and detection methods were developed. And this means that you could detect the phase of light. And on the right-hand side, you'll see a conceptual diagram where light is shown as a wave, and you see different types of phases 90 degrees apart. How can you change the phase of light? There's a very simple, clever method for that. You take a laser beam, you split the laser beam. One leg goes without interruption. The other leg goes through some kind of medium. Could be glass, could be a crystal. And the speed of light in that medium will be slower. Light is being slowed down when it goes through glass or through a crystal. And after that, you combine both signals, and the delay of one part of the light will introduce a phase change of light. And if you apply some kind of voltage over that medium, you can control how much delay and how much phase change is being introduced. And this way you can modulate the phase of light. In the example, we have 4 phases. This is called quadrature phase shift keying. And what you can do is you can create a diagram, which is shown at the bottom. This is called a constellation. And in the diagram, you see 4 dots, and each dot corresponds to one phase. The angle around is the phase, and the distance to the center is basically the intensity of the light. It's the light power. So you can see that with 4 symbols, you can encode 2 bits. You have one symbol 00, 01, 10, and the final symbol is 11. That is QPSK. You can also have other types of modulation. So at the bottom right, there is another example, 16 QAM. 16 QAM means 16 symbols. It means phase and amplitude modulation, quadrature amplitude modulation. And the 16 symbols can therefore encode 4 bits. You can go from 000 to 1111. And you can see that there are different phases, but also different distances to the center. So you have different amplitudes. One thing to keep in mind, and this is basically covered by Pascal and by Lydia before, is that you have noise in your system. So these symbols, they will not be detected perfect like this. They will go up and down, that is the noise. Or they may switch around a little bit, that is phase noise. And the other thing is that both Lydia and Pascal introduced nonlinearity. So if you have too much power, at some point, the performance of your system will go down. And remember that the outer symbols are the ones with the highest power. This means that they will incur high nonlinear penalties or impairments compared to the symbols who are more innermost. And those are things to keep in mind when we continue with the next slides. The second basic introduction I would like to share with you is the data capacity of these signals. So we have wavelengths traveling over or through the fiber pair. These signals have a data rate, and the data rate is nothing more than the amounts of bits per symbol, which we just saw, the modulation, times the modulation rate, how many symbols per second you can transport. If you multiply the two, and for the example of QPSK, we have 2 bits per symbol, and if we assume a symbol rate of 25 gigabaud, Baud was a French engineer who did some first encoding, you get to 50 gigabit per second. Note that the spectral width, so the amount of spectrum a data signal occupies in the spectrum is proportional to the baud rate. So if I have 25 gigabaud, it means that my signal has a width of 25 gigahertz. And usually it's a little bit more because of imperfections, but that is actually something to keep in mind. Now, I think Pascal also introduced the concept that you have polarization in light. You have actually two perpendicular orthogonally polarized directions. And we can encode each of these polarizations independently. So that means that for our wavelength, we can actually double the capacity from 50 to 100 gigabit. However, the 100 gigabit is not sufficient. If you really want to transport 100 gigabit, we need to encapsulate the signal to allow for performance monitoring, for alarm propagations and other things. So we need OTN or Ethernet encapsulation, which requires more bandwidth. And then on top of that, we want, of course, that the signal arrives without any errors. So we need to have some kind of forward error correction mechanism that will take care of correcting all the errors which might happen during the transmission. And all of that together adds more overhead. And to transport 100 gigabit, one would need actually 132 gigabit net data rate. And to do that with QPSK, you need 33 gigabaud. And that is actually, I think, something that Pascal and Lydia mentioned as well. That is a very standard transmission coding signal. So the two key takeaways are, if you see higher bit per symbol, it means you can get more capacity in your cable system. But if you see a higher baud rate, that does not mean more capacity in your cable system. It just means you have a higher line rate, but you don't have more capacity. And if you have a fixed data rate, so if you have a fixed 100 gig, 200 gig, then by increasing the baud rate, you need less bits per symbol. And if you have less bits per symbol, it means that your signal is more robust, because you might have noticed in the previous slide that the 16 QAM symbols are closer together. The space in between is smaller than for QPSK, which means that they are more sensitive to noise. And if you would increase them by increasing the power, you get problems with nonlinearities, as explained. So there's a limit to what you can do. Higher modulation means more susceptible to noise because the symbols are closer together. Less bits per symbol means you are less sensitive to noise, and therefore you have a better reach. So having said that, what is the coherent transponder technology evolution over the last decade? So it started around 2010. We had QPSK, we had 33 gigabaud. That was the first generation that could modulate about 2 bits per symbol. And over the last 12 years, we have progressed to 800 gigabit per second line rate, using 100 gigabaud and using 64 QAM modulation. So that is a significant increase. It means that we have an increase of the line rate. And if you have a higher line rate on a transponder, it means you need less transponders for the same capacity. It means lower power consumption, less floor space, and lower cost, of course. And in addition, we have increased the spectral efficiency, the number of bits per symbol. And therefore, we have managed to increase the capacity of cable systems. And that's very important, because the cable systems have long lifetimes of 25 years. So while we are talking about petabit cable systems, we should not forget that there are many cable systems who are just a few years old, or 10 years old, or even 20 years old, that we want to maximize. We want to maximize the assets and the capacity. We want to maximize revenue. So by using transponder technology, latest transponder technology on all the cable systems, we can actually monetize older cable systems in a good way. Oh, wrong button. So this is the architecture of a modern 800 gig transponder system. And Without going into too much detail, on the left, you will see the same type of architecture I covered in my first slide. Light is being split into polarization directions, and then these polarization directions are being phase modulated, and the bit stream is provided by the digital analog converter and the driver. On the receive side, a polarization beam splitter is being used to split the polarizations, and then to make it a coherent receiver, we use a local oscillator, we use a local laser, which is mixed with the signal that arrives. And in this way, we can actually determine the different phases of the signals, which goes through photodetectors, through transimpedance amplifiers that convert the current into voltage, and then through an analog digital converter into a digital signal processor for further processing. And you can see that these components all have different colors. Some are photonic components, some are analog, some are digital components. What's important for best performance is that these components have the right materials, like indium phosphide, that really perform very well at these high speeds. And they have very little noise and minimized distortions. So the integration of all these components is very important. It's a key element for good performance. Integration and packaging everything together. So during the last two generations, the fourth and the fifth generation, we introduced a new type of modulation, which is called probabilistic constellation shaping. And the importance of this is that you get much better performance and much better capacity. Traditional modulation, if you look at the top right-hand side, traditional modulation was very much a step function. You would have, for example, 16 QAM, 4 bits per symbol, and at a certain reach that would not work anymore. So you would need to use a lower modulation, like 8 QAM, you get 3 bits per symbol, and you can get further, and at some point it does that does not work anymore. You go back to QPSK, you get 2 bits per symbol, and so on. So that's very much a step function. What if you could actually, and of course, the disadvantage of that is that if you happen to have the wrong reach, you would certainly just cut off and lose a lot of capacity. What if you could have a smooth curve throughout the whole reach? What if you could not have 4, 3, 2 bits per symbol, but 4, 3.9, 3.8, 3.7, and so on? And that is basically what probabilistic constellation shaping does. If you go to the left-hand side, top part, what probabilistic constellation shaping does is it takes a large constellation, 64 QAM, but not all the symbols will happen with the same probability. Some symbols, the ones in the middle, they will happen more often. Those bits will happen more often. The ones at the outside, they will happen less often. And that's a very special way of constructing your modulation symbol. Of course, it means you have, in total, you will have less bits per symbol. That is the, that's the probabilistic constellation shaping part. That's the fractional bits per symbol. But you will also use less optical power. So you can put these symbols further apart. So you get better OSNR, resiliency. You can incur more noise, and you also have less nonlinear penalties because the outer symbols with the most power, they will not happen most. So in this way, you get a better performance. The special ingredient is, of course, how do you map your bit stream, which comes in? How do you map that into this new distribution of symbols? How do you determine that some of the bits will happen often and should be put in the middle, and that some bit sequences do not happen often? That is called the distribution matcher. It's a very complicated mathematical algorithm, and it needs to be done in real time because you get a stream of 800 gigabit per second, and that algorithm will look into the future. It will look at the next bit stream that is called the code length or the code worth, and that bit sequence based on that bit sequence, it will determine a kind of mapping from bits to symbols. And it does that in such a way that the ones in the middle will appear more often and the ones at the edge is not. And it has overall, it has a Gaussian shape, Maxwell-Boltzmann shape to be precise. So that is a code word and that is a distribution matcher. And the longer the code word, the better the translation is, the better the performance. So PCS brings us improved tolerance to noise and nonlinearities. It will bring us better capacity, spectral efficiency, and reach. And therefore, it's a technology that is more or less implemented on all new generations. So we have additional benefits with new technologies. One is very high baud rate. You know, we go towards 100 gigabaud at the moment. And you will recall from the first slide that if you have a high baud rate, you need less bits per symbol to get to the same line rate. And this is an example calculated for a transatlantic cable system. On the vertical axis, you have the distance. It's a transatlantic cable system, so one is 7,000 kilometers. And on the horizontal axis, you have the baud rate, the symbol rate. And you can see that for 500 gigabit and 600 gigabit, if you increase the baud rate, the reach will go up. In fact, just going from 96 to 100 gigabaud, which is seems to be a tiny increase, will actually increase your reach with 20%, which in this case, it's about 1,400 kilometers. And the dotted line, that shows the spectral efficiency. So while the baud rate goes up, the dotted line goes down. So the product remains the same. In addition to very high baud rates, you want to have variable baud rates. And why is that? And again, I thank Pascal for kind of saving me a lot of explanation. In a nutshell, you will remember that you have a quality factor. And if you look at the spectrum of a subsea cable, you will have the so-called FAC limit. You want a performance that is above the FAC limit, so it's error-free. And on top of that, you want to have some operational margin to protect against aging and repairs. So you will have a certain commissioning limit. And above that, the quality of your signal does not really provide much value. It's an unused margin. Now, the performance of a cable system, even though the OSNR is flat due to nonlinearities, typically the red side, the lower frequencies, will perform somewhat better than the blue frequencies. So if you start to deploy, you will put a wavelength on the blue side, which complies with your minimum performance. And you continue, and then you will see that your signal strength, your Q quality factor, will just increase along the way. But your modulation will remain the same. The baud rate is the same, and the spectral efficiency remains the same, because if you go from, say, 300 to 400 gigabit, you want to increase the line rate, you mean that from 300 to 400, you need to have 1/3 more line rate. So you need to have 1/3 more spectral efficiency if you keep the baud rate the same. So you would need to go from 6 to 8 bit per symbol, which is quite a lot, which is not going to happen on a modern good cable system. However, what you can do is you can change the baud rate slightly. So you go from the right-hand side and then slowly to the left, to the better part of the spectrum, you increase the bit per symbol slightly and you decrease the baud rate slightly so that the line rate remains the same. And then what happens is that because the baud rate is increased, the spectral width is less, which I mentioned at the beginning. So it means you can put more channels into the spectrum. So it means that even with the same line rate, you get more capacity. In this way, you can increase capacity of the cable system. And we have many examples of how it looks like in real life. This is one real life example of a system, and you can see that purple is a low spectral efficiency, and going to green, yellow, and red, you get high spectral efficiency, and you can see the performance going from top left to bottom right. And what you can do is you can take in each part of the spectrum, you can take the maximum spectral efficiency which works best in that part of the spectrum. But keep in mind that the higher line rate does not mean that you have a better spectral efficiency. So higher baud rate by itself does not improve capacity over the spectrum. In addition to these, we have in our toolkit some other technologies which will help to maximize the performance in a cable system. Modern 5th generation transponders use typically Nyquist shaping of carriers. What that means is that a conventional laser, if you put a laser on and you put some capacity on that laser, the laser will have some kind of shape with a certain roll-off. What can be done in modern transponders is that the digital signal processor will shape the signal to be very square, which means that you can put these channels very close to each other because there is hardly any roll-off, so you don't need to worry about overlap and crosstalk. That is the Nyquist shape. And then on top of that, one single laser signal can actually be divided in multiple digital signals or carriers, each of them having a smaller line rate and baud rate. So for example, 800 gigabit can be divided in 8 times 100 gigabit signals. They behave as independent carriers, but they are powered by one laser. And this has many advantages in terms of performance. Another interesting example is if you have an integrated system where you have your lasers, multiple lasers working with a single digital signal processor, you can actually apply your forward error correction over multiple wavelengths. So the advantage of that is that you can put one wavelength in a good part of a spectrum where it incurs not many errors, and you could put one carrier in a bad part of a spectrum. And that other carrier in a bad part of the spectrum would normally not function. It would probably require lower modulation, less capacity, but you can load balance the forward error correction algorithm over 2 different wavelengths. And on your right-hand side, at the bottom side, this is a real-life deployment from this region on a cable system. And you see a spectrum from left to right. You see the blue dots. Hopefully you can see the blue dots from the back. And the blue dots, they go down from the edge to the middle, because the middle is the worst performing part of this cable system. And if you go below a certain threshold, it does not comply with minimum specifications. So what we can do, and what we did, is we take the leftmost best performing part, and we pair that wavelength with the rightmost worst performing part, and together they are averaged. And if we do the outermost, if we pair the outermost channels and then the second ones and all the way to the 2 innermost ones, you get the red dots. And the red dots show that you get a nice flat performance. So in this way, we electronically compensate for the large performance change slope in the system. Let me introduce to you 2 more examples of how the transponder technology can maximize performance in a system. And I would like to remind you that these technologies are not just for new cable systems, but actually quite useful for older cable systems as well. They maximize the value of all the cable systems. So on the top, we have multi-dimensional modulation formats. We mentioned the constellation before, and if you have a traditional constellation, you have outer points and inner points. Outer points having high power, inner points having lower power. And of course, if you happen to have lots of symbols which happen to be consecutively at the outside, your signal will be quite powerful. And as a result, it will incur high nonlinear penalties. So what you can do is you can modulate the signal in a very smart, intelligent way. You can make it such that the X polarization might have an outer symbol with high power, but that the Y polarization will then have a lower power and vice versa. So you kind of correlate high power with lower power over the two polarizations, as well as over the subcarriers. And this is called multidimensional 4D, 8D modulation, because you have the phase, you have the polarization, you have the subcarriers. And the result, and this is again a cable system from this region. The result can be seen in the top right. So we have a spectrum. We see on the left-hand side, we have carriers, which we monitor. And blue, again, blue is standard probabilistic constellation shaping, and the center of the spectrum is the worst part. So you can see that from the edge, the blue dots go down, and at a certain moment they are below a certain minimum quality and does not work anymore. And by introducing these type of multidimensional modulation formats, we see suddenly that for exactly the same capacity, 400 gigabit per wavelength, we get a very flat performance. So this is a very robust way to filter out the penalties of high power nonlinearities. At the bottom, we have a final modulation technology. This is called super Gaussian probabilistic shaping. Probabilistic constellation shaping follows this Gaussian curve of symbols, outer symbols not happening often, and inner symbols being more prominent, and then ramping off again. You can imagine that if you have a very high power system, like a top racing circuit, then even the outer symbols will be quite powerful and contribute a lot of nonlinear penalties. So maybe you want to tweak the shape to be that the slopes are less and that the inner part is a little bit higher. So you get from the dashed red line, you get more like the blue line, which is smaller and more flat. And this is called a super Gaussian because the Gaussian has a power, which is the power of 2 squared. And you can change that to 2.5, 3 in the mathematical formula. And the result can be seen on the right-hand side. This is for Maria. This is a top transatlantic cable system. And you can see that the red curve, which is the Gaussian order 2, and then subsequently the green and the blue are getting higher, which means that you get better quality by applying this super Gaussian. At the top, with Gaussian order 3.5, actually it goes down. So there is a certain optimum performance. So I hope you are not dazzled by all of these descriptions, but this slide shows you that modern transponders have a toolkit with many different technologies, most of which I actually already managed to cover for you. And this toolkit is like a toolkit of a mechanic or a craftsman, and it does not, a good craftsman will not use the hammer to put in a screw, right? You need a screwdriver for that, and you use the hammer for the nail. And the thing to remember is that all these technologies will maximize performance on different type of subsea cable systems. And some cable systems are already 20 years old, even 25 years old. Pascal mentioned that the lifetime of a cable system are 25 years old. I can tell you, we have been approached by customers who have a cable system which is 25 years old, but actually it's still working, and it's still working fine. And you can therefore sweat your assets. You can get a lot of revenue, and all your assets are already written off, and therefore it's very low cost. I don't know about maintenance though, but so you can use all these different tools to apply for all the cable systems, new cable systems, and future spatial division multiplexing cables. And the result is that we see record performing capacities and performance with the newest or the latest generation technology over all these different cable systems, whether it's the high performance Maria cable systems, the top left, which is transatlantic, which can achieve 30 terabit of capacity over a single fiber pair, or whether it's a modern spatial division multiplexing cable like Dunant from ASN, where we can achieve 25 terabit of capacity, over 25. So that's actually not much less than Maria, but it has many more fiber pairs. So the fiber pair capacity is a little bit lower, but the cable capacity is much, much higher. Or even on the bottom right, where we have a very old system, more than 9,000 kilometers, we increase the design capacity by 10-fold. And what's even more important, we actually allow 400 gigabit services to be transported over that system. So it is completely future-proof. So let's look at the future. Where are we now? I will not cover the Shannon formula. I think you've seen it now already a few times. But there is a bandwidth term and there's a log term. And some things, some improvements in the future have to do with the bandwidth term and some have to do with the logarithmic term. Currently, and this is calculated for a specific cable system, but currently cable systems are at approximately 70% of the theoretical maximum capacity. I'm not saying it's actually possible to achieve the theoretical maximum capacity. I'm saying that there is a gap of about 30%. And in the past, we have seen when we went from on-off keying to coherent, we saw a 10-fold increase in capacity. And then when we went from first generation to let's say third generation, we doubled the capacity, and then we went to fifth generation and we got 30% more capacity. And in the future, these increases will be smaller because we crawl towards the Shannon limit. And the gap that we see, the 30% gap, can be divided in trying to perfectize the nonlinear compensation. Nonlinear compensation is currently seen, it's a very complex physical behavior. It's treated as a noise, but actually it's very well understood. It is very deterministic. You can calculate it. You can calculate very precisely how it works, and you can therefore try to backwards calculate how it needs to be compensated, but that's very, very complicated. There's the perfect FEC. You know, what happens if a cable system is just better, then you don't need all that forward error correction, or what if you can get better encoding efficiency? And finally, there is perfect filling and zero margin. So, and there's actually a few things so some of these things we as a supplier or a technology developer, we try to improve, but actually there are some things that you already can do right now. For example, 90% of traffic, subsea traffic, is Ethernet based, but traditional operators like to have 100% OTN technology. And that has to do with interoperability and monitoring and so on. But if operators would change towards using Ethernet framing, you get 4% more capacity. And remember that Dunant transatlantic cable system, 25 terabit, 4% means you get 1 terabit of extra revenue, just by deciding I don't need OTN, or I only need OTN for 10 gigabit traffic, which is dying out anyway. And another thing you can do is you can reduce your operational margin. Currently, what is happening is we have the FEC limit, and then we put aging, repair, we calculate how much repair do you have over 25 years. That's a lot of repair, right? And studies have shown that aging of fiber actually happens within the first few years, and maybe Lydia can confirm, but that is what I remember. So, and then on top of that, people just want to be absolutely certain that nothing will happen, so they have an end-of-life margin, which kind of doubles it. What you can do is you can say, right now, the cable is young, has no repairs, has optimum performance. I take a minimum amount of margin, I get the maximum capacity. And then over time, well, I will monitor the cable performance very closely. You know, I do some learning, machine learning, and we try to kind of project the change in performance. And if necessary, I will then adapt my modulation and my capacity. So you go from best capacity to worst capacity, instead of going from capacity what we can do now and then keep that the same over time. But that requires a mind shift. And obviously there are some operational implications. You know, what happens if something, if you have a repair, you need to make changes and so on. But these are things to be considered. So my second part of my talk is about approaches to subsea cable systems. And I know that we are getting to the top of the hour. I had a conversation with Bartosz, and my understanding was that, you know, as long as you're still sitting and listening to me, it's okay to continue. So my apologies if I take a little bit more of your time to finish off my talk. So again, going back to what Lydia and Pascal mentioned, we have new types of cable system, spatial division multiplexing, which means you have high fiber count. And also mentioned by Pascal, we have open cable systems. We can choose what type of technology to put over it, what kind of car to race. Or maybe you want to have, maybe you have a big garage, you want to have a Ferrari and a Porsche. So in addition to traditional selling capacity or even selling fiber pair, there's a new product, which is spectrum. But selling spectrum comes with responsibilities. So without going into too much detail, this is the architecture of a submarine line terminating equipment terminal. There is a WSS, which is used to scale the amount of channels and also to allow certain channels to be put in certain parts of the spectrum. And there is a noise loading source, and the WSS can put the noise loading source anywhere in the spectrum. And then you have transponders, which are tunable. The most important thing, which maybe was not explained so far, but in a terrestrial system, if you get more capacity, you can just have a control loop and you just turn up the power of your amplifier. You have more gain and more power. In a subsea system, all the repeaters, submerged amplifiers, they all work on constant power, which means that your spectrum always needs to be occupied. If you don't have channels, you need to put something else, which is AZ, amplified spontaneous emission, which is a noise source. And cable systems have become more complex today. And this is a rare animation. So here we have the cable landing station. You do spectrum sharing. So in your landing station, you have your transponders, but you also have a spectrum customer, tenant A, tenant B, who also have transponders. Transponders can fail, not your transponders. You don't have an alarm. Someone else's transponder fails. As mentioned by Lydia, she did a study of what type of fiber pair gives you the best performance if you backhaul this to a point of presence or a data center inland. So we have a terrestrial backhaul network, and we have transponders there as well. And the network, the backhaul network, is maybe some kind of complicated mesh or ring. So things can happen there as well. Transponders can fail there. Terrestrial backhaul fiber pairs can fail as well. And then on top of that, we have these modern branch units, and branch units can fail as well. So there are many things that go wrong as networks become more complex today rather than point to point. Why is that important? It's important because submerged amplifiers, the repeaters, they work on constant power. Let's assume we have 8 wavelengths, and let's assume we have a repeater, an amplifier, which applies 8 units of power. So all the wavelengths are being amplified. What happens if something goes wrong, as shown in the previous slide? If a transponder fails, and we miss a number of wavelengths. The repeater will still apply the same power, but now the total power is divided over the remaining wavelengths. So each wavelength gets more amplified. If you are still in the linear regime, as shown by Pascal and again Lydia, that's fine. But if you are quite close to the top, I remember in one of the slides, I think it was Lydia's slide, that you need to be like, you know, and in a specific case, it was recommended to be like 2 dB below the top, but it can be higher. Then what happens, depending on how many wavelengths you lose, what happens is that the remaining wavelengths get too much amplified and the performance goes down. The power goes up, but the Q goes down. And these channels will incur errors. So in order to deal with that, you need to have some kind of detection mechanism, a monitoring and detection mechanism, which will detect that something is wrong in a spectrum. There is a threshold, there is something missing, or there's already maybe something is too high. And then upon detecting this, we'll then recover by replacing the missing part of the spectrum, or by blocking that part and then replacing it with the right type of power and from some kind of noise source. And then this will lead to recovery of the whole spectrum. And then you can recover the channels when everything's okay. So this type of spectrum protection and restoration functionality is required if you want to sell spectrum. And the two key factors that people sometimes do not realize is that we, and Pascal mentioned, we go from 33 to 100 gigabaud. So it means that our channels become 3 times bigger. So if you lose one channel now, it's like having lost 3 channels before. So the problem of losing a channel or a failing transponder, which can happen, is actually going to be multiplied, and baud rates are going to be up. And the other thing, which I mentioned in one of my previous slides, is you don't get signals with high power anymore. You want actually your signals, sorry, high Qs, you want your signals to be exactly your commissioning limit, because then you get the maximum amount of capacity. But that means that, and if you want to really maximize your capacity, you want to make your commissioning limit, your Q levels, as low as possible, because that's what I mentioned. That's a way of maximizing capacity on your cable system. But of course, that means that if something goes wrong, then these carriers are very susceptible to errors. So you get a high capacity engine, you get a Ferrari, but your racetrack needs to be very, very flat. You cannot have bumps. If you have a bump, you need to smooth it, and that's basically the protection restoration technology. So what does that mean? It means you have different, if you have a fiber pair and you want to sell spectrum to your customer, or maybe you are a customer, you want to lease or buy spectrum from a fiber pair owner, there are different models to consider because it's an open cable system. So in orange, you have the fiber pair owner. Orange is the spectrum portal. And then through the spectral portal, which monitors the spectrum, which can do the spectrum protection and restoration, which we showed in the previous slide, we have either a customer who attaches transponders directly, or we have a customer who puts an SLT with its own power management configuration. So the difference is that the green customer is cost effective. It puts in its transponder, it does not need any more equipment, and it relies on the fiber pair owner to protect the spectrum. The blue customer, with that type of solution, you consider your spectrum as a virtual fiber pair, and you can do everything in that virtual fiber pair yourself. You can increase channels, decrease channels, because you fully manage the power inside. And of course, the fiber pair owner is the entity that finally monitors and controls the full fiber pair. And basically it looks like this, where, for example, tenant B gets a block of a spectrum. Tenant A just adds wavelengths, and the fiber pair owner has its own wavelengths. And the combined spectrum is going to be a mix. And what's very important in this case is that if you have spectrum protection and restoration, you try to make it very granular. You do not want a large block being protected, because if, let's assume some wavelengths are missing, but some other wavelengths are still functioning, and then the technology just blocks everything. It goes, it blocks the thing that hurts, but it also blocks the things that's still working. So what you want to do, ideally, you want a technology that even though you have one physical port to connect, that it can still monitor and replace spectrum with small slices down to a single line module. So this means that if you are into spectrum management, and by the way, the tenant with its own solution, the tenant does not fully control the full spectrum, but the tenant does control its own part of the spectrum, and it can actually do spectrum protection restoration on its own part as well. And therefore you have the industry, the market requires new type of functionality, software, intelligent spectrum management software, which can, for example, view a spectrum, which can transport a spectrum over the terrestrial backhaul. It can protect and restore the spectrum. It can share the spectrum. It can make certain that you do not go outside of your spectrum boundaries. Protects against branch failure. Measures GSNR, OSNR, as mentioned by Pascal. That is the way how new cable systems are being measured in terms of performance, and maybe even allow you to do your own deployments. So in summary, 5th generation technology provides a toolkit which significantly increases performance. And this is not just for new cable systems. This is even more importantly also valid for existing older cable systems. And open cable systems allow easier upgrades. So you can pick and choose what technology to use. You want a Ferrari, you want a Porsche. But you need to be able to control what's going in, and you need to be able to make certain that one part of the spectrum, which is maybe used by the operator or by a certain customer, is not impacted if something goes wrong in a different part of the spectrum, which might actually be in a completely different location. So you need spectrum monitoring protection functionality. And if you have time, and if you maybe get access to this presentation, there are a number of brochures, application notes, and interesting papers. And if you like technology, these papers, Infinera marketing is typically very much about trying to explain how technology works. So if you like that kind of thing, feel free to find this presentation or contact me, and I'll help you with these white papers. Thank you.
Wow, Alan, very impressive. Thank you so much. That was last but not least, but that was again a huge amount of knowledge which has been shared here with the masterclass. So thank you for that. Shall we check if there are any questions? What do you say?
Let's see if they're still awake.
Okay, are you awake? In the back, completely in the back, we have there. Yeah, wake up, Bartosz. Now you need to run. Check.
Hello. Excuse me, I read about the PAM4 line coding and how the mechanism of this system working for coding, and how this one reduce the error, as this is used, I believe, in Infinera CHM6, this coding, plus how this compatible with another vendor, if we can say open line system, how this compatible?
Well, this is certainly swimming in deep water immediately.
Because, sorry, I test this one and this error-free, this is a success story, yes. We're working together at this.
So Infinera 5th generation technology uses soft decision forward error correction. The The actual coding is proprietary and it's kind of a company secret. Generally, the vendors, they use the same type of generation of or similar modern generation technologies, but they will need to make certain decisions. For example, do you want to, so you have, forward error correction has a certain coding gain, and the coding gain basically tells you how many errors can be corrected. Do you need a high coding gain, or is a low coding gain enough? Is sufficient? If you need a high coding gain, this means you will need to have a lot of overhead. So your 100 gigabit can become a 200. So for 100 gigabit transport, you might be required to transport the double amount of capacity, which is essentially a waste unless you actually need that. So I cannot answer your question precisely. First of all, I have to admit, I don't know exactly what precise, because I sense from your question that you want to hear a precise answer in terms of the coding technology. And that I don't know. And also, even if I would know, it's something that is typically not shared. I can tell you two things which might be of interest to you. One is our forward error correction is adjustable. So we can actually adjust high and low coding gain. And low coding gain has the advantage of using less overhead. So that's basically being used if you don't need much forward error correction. And high coding gain is then being used for very challenging links, which you just want to close with a certain, you don't mind about capacity, but you just want to make certain you connect at a certain line rate. And the other interesting thing maybe for you to consider is that high forward error correction might not be the best solution, because we have seen that probabilistic constellation shaping kinds of tries to maximize capacity for what kind of performance you get. So rather than having a high forward error correction coding gain and then using lots of overhead, which might not be used, you actually want to kind of minimize that. And then just let the probabilistic constellation shaping give you the max capacity under these circumstances. Having said that, I'm certain, and I know that next generations, we're talking about 6th, 7th generation, will have forward error correction coding gain improvements. I hope this answer helps you.
Okay, thank you for your question, sir. Any other questions?
I have a question.
Thank you, Lydia. Thank you for saving me. Please.
So, Alan, you show a very nice slide of the evolution of Korean technology over the years. So my question for you, do you think so I think I can assume that next generation of transponder is going to have higher baud rate to increase transponder data rate. But do you think spectral efficiency, you can continue increasing the spectral efficiency of the transponders, and how?
Thank you, Lydia. Good question. Two answers. Baud rate will increase for certain. We see, so the DSPs are using CMOS technology, and although 5 nanometers, so currently 7 nanometer CMOS is being used in the industry's transponders and digital signal processors. And we see a trend that when CMOS-based coherent digital signal processors are becoming available, 5 nanometer, 3 nanometer, this will increase baud rate to 140 gigabaud, and then with 3 nanometer up to 200 gigabaud. So that means that we can actually double the line rate. And to answer a previous question about, I think, power consumption, we think that we can double the capacity on a module, on a transponder, with the same or even less power consumption. So we don't increase the floor space, we actually lower the power consumption, and we double the capacity. So we actually, the power consumption per bit is halved. Going forward, recently there was a conference, a European conference, optical conference called ECOC, And during ECOC, there have been presentations regarding hero experiments. Currently, in a laboratory environment, baud rates of up to 260 gigabaud are being achieved. This requires really good and maybe new materials, lithium niobide, plus what's the name? Nano. So it's a portmanteau of plastic and electronics. So plasmotronics or plasmonics, something like that. So I think it's nanoplasmonics. So this is basically polymers used as a semiconductor. And the industry thinks that with this type of technology, we should within 10 years be able to achieve possibly 1 terabaud. So that is mind-boggling. It means that with that type of technology, you maybe need 4 or 5 transponders and your whole spectrum is full. So I think, Lydia, that answers part of your question. The second part is about, yes, we go to a higher line rate, but higher baud rate does not improve capacity. It just improves the economics. So we are working, when I say we, I mean the industry as a whole, we are working on optimizing nonlinear compensation by, for example, machine learning. We are trying to optimize fault error correction algorithms. We try to reduce the roll-off so that we try to make these channels as square as possible so that we can squeeze them together. We don't have unused space. And I mentioned that in the last decade or so, we have seen capacity first multiplying by 10, then doubling, then 30%. And I would say, Lydia, that within the next 2 years, we probably will see another increase of spectral efficiency of maybe 20%, can be a bit less, can be a bit more, depending on the cable system. So we get from 70% of Shannon, theoretical Shannon limit, we get another 20% on top of that. So we get to 84% or something like that. So and maybe the generation after that, we will have another 10%. So we get from 84% to 92%. And then I don't want to, I don't dare to project anymore, but those are my expectations and probably before the end of this decade, Lydia.
Okay, these including nonlinear compensation and FAC optimization, better FAC design.
Yes, and as mentioned before, there are also things that the customer can do, like lowering operational margin and using a better, more efficient framing. OTN is not really required, so you have less overhead.
And Alan, do you think for those next generation of CMOS technology with 5 nanometers and 3, you can maintain the effective number of bits over those baud rate that you have mentioned, 140 gigabaud and 200? So the plan is planning maintain the effective number of bits.
Yes, likely. Yeah, likely it's likely possible that maybe initially with the next generation, we just go to higher baud rate and we maintain or improve spectral efficiency. I think when you go from 7 to 5 nanometer, but then when you go from 5 to 3 nanometer, your DSP has many more gates, and that will allow you to implement more advanced algorithms. And then I expect, so first the focus will be on increasing baud rate, and then the focus will be increasing baud rate and spectral efficiency. And obviously, when I say 5 and 3 nanometer, different vendors are implementing different product strategies in terms of some are maybe skipping the 7 nanometer to go to 5, some might be skipping the 5 nanometer to go to 3, some might go from 7 to 5 to 3, and so on.
Thank you so much.
You're welcome.
All right. Any other question? Last one. Come on. There is one for this gentleman over there in the middle.
You are like an auction.
Yeah, I know, but Sometimes you have to.
Thank you very
because,
much. Can we know the threshold, distance threshold for the 5th generation without regeneration?
Could you repeat the first part of your question?
I mean, the distance threshold for the 800G lambda.
The distance
Yes.
without regeneration.
Yes.
So that very much depends on the system. I need to be very careful here, but because I'm not certain if this has actually been published, but I am pretty certain we achieved 800 gig over 2,000 kilometers. And that's enormous impressive. Before, when we introduced 800 gig, so now I'm not talking as a representative of the industry, now I'm talking as a representative of Infinera. 800 gig was already on the market, but performance was not really well known, probably a few hundred kilometers. And Infinera 5th generation 800 gig mentioned to go to achieved 800 kilometers, and then this was slowly improved with 100 gigabaud. And as I mentioned, 100 gigabaud gives you, and then obviously it depends a little bit on the system. 800, maybe even 1,000 kilometers. That's absolutely a real life deployment. To go to 2,000 kilometers, I think that was kind of a lab performance where we put the amplifiers on very good spacing. We use the best type of fiber as indicated by Lydia, and in this way, I know it has been mentioned in a conference, but I don't think it has been published. Or at least we kept it quite low profile, to be honest. Yeah.
The other question is related to the spectrum controller.
Yes.
You know, the port supported by the spectrum controller is reciprocal with the, cable capacity. In other words, how many ports supported by the spectrum controller?
So of course the spectrum controller depends on the technology you use, right? Every vendor has a different type of spectrum controller, and it's basically the wavelength selector switch module, which has the number of ports which are being used for spectrum controlling. In the case of Infinera solution, we have 20 ports. So one port is being used for AZ source. 19 ports are available to attach 19 customers, which obviously is, well, plentiful. The first part of your question I did not fully get. So maybe can you repeat that again?
Well, it is same. Same. How many ports supported by the spectrum controller?
How many
ports?
Yeah,
you answered it. You answered.
So I did answer it. Okay.
Yeah, you answered.
Yeah. Okay.
Thank you.
I thought you had two questions. I did understand the last part. Yes. Okay.
Thank you very much.
Yeah.
Any other volunteers? Then please, Alan, embrace your applause.
And I would like to applaud for having you still here at this time. Thank you very much for your patience. Thank you.
Thank you so much, guys. And with this, I also would like to thank very much Lydia. Thank you so much. Hope to see you soon. Thank you so much for being here with us, staying almost 3 hours with us here, and then sharing your knowledge here in the masterclass with the complete GCCM here in the Middle East, in Oman. So thank you so much.
My pleasure. Thank you for having me.
Absolutely a pleasure. It's all ours. Thank you. And Pascal, merci bien. Thank you so much. And ladies and gentlemen, as Alan already said, and he's right, almost 3 hours knowledge sharing masterclass sponsored by Omantel. We would like to thank you so much. We had 2 days of quite intensive talks, meetings, network session, knowledge sharing, masterclasses, what have you. I would like to thank you for your attention. We did it happily. We did it gladly. We're proud to do it for you. And we wish you all the best. Enjoy the rest of the day and evening.